I have just recorded the Exam 2 review, which will go up today. I'll send the link out to everybody who's taken the exam. We are moving on to Chapter 9. I haven't posted the study guide yet, which I realize is a problem. I realize that your next exam is scheduled for June 6th. Just to give you a sense for where we are maybe 3 lectures behind in terms of where I expected to be. So I think what I'm going to do on exam 6 is push it back a week if I can. That may be a problem for some of your schedules. If it is, I'm willing to work with you. The one thing we can't push back, unfortunately, is the final. That's like a hard deadline that we can't deal with. The finals week, by which they mean finals 2 days, is June 15th through the 16th. Okay, so there's going to be things in these last few chapters that I usually cover in a lot of detail that we're not going to. I don't think that's going to be a detriment to you in 352. Some of the mechanisms we learn will be important in 352, and we'll talk about those. The ones that won't, we won't talk about in a lot of detail. In terms of pushing the exam 3 back by 1 week, I'm going to need to talk to the testing center and see if I can schedule that. I will let you know as soon as possible when that is. And like I said, if for whatever reason the new date is not something you were planning on and therefore you need some flexibility, please contact me and I'm willing to help. All right? Study guides for this next section up to exam 3 will be posted later today as well. My intent is to do much of chapter 9 today, and then we'll just go on from there. Any questions you want to ask? What is my excuse for not having it up yet? First, excuses don't matter, so I guess I don't have any. But as I've mentioned before, I've been working really hard on this research project to model proteins computationally, and I got really close to learning something, and then I discovered I had made a mistake, which is requiring me to go back about a whole week and redo some stuff, and I got ticked off. And anyway, but that shouldn't harm you, and so I'm hopeful that by pushing the exam back, I will pay for, in some ways, my failure to get things posted in time. All right, questions? No? Yes? Okay. All right, so I just wanted to show you, and this is not something for you to memorize or worry about scribbling down, but I wanted to show you a couple of biological examples of some of the reactions we've been dealing with. So here is a precursor to adrenaline. It's called noradrenaline. And the difference between adrenaline and noradrenaline is this methyl group. And so if you wanted to make this in the lab, one of the ways you could consider doing it is just using an alkyl halide like methyl iodide. And you would hope you'd have to count on the idea that nitrogen is more nucleophilic than oxygen, and you could hope to make this molecule. Now, there's some other problems associated with that we're not really worrying about at this stage, but biology doesn't use methyl iodide because methyl iodide is not selective. It will methylate all biological nucleophiles. And so if you want to methylate your DNA or methylate groups on the protein surface of various enzymes, this would be a great reagent, but that's not a great thing to do in terms of functioning biology, and so this is toxic. So nature uses a different system for SN2 reactions where you transfer methyl groups, and this is nature's methyl iodide, and its name is SAM, or S-adenosyl methionine. You don't have to worry about what all of this means. Here is the adenosine part. This is the adenine base. Here's a ribose sugar. In gray is the adenosyl from adenosyl methionine. In green is the methionine part. And the business end of this molecule is right here. You have a methyl group attached to a positively charged sulfur. The sulfur's bonded to 3 different things. So it's positively charged just like oxygen would be when bonded to 3 different things. But you can think of all of what's in yellow here as a good leaving group. You can see that if it left, it would leave as a neutral sulfur. And perhaps some of the other stuff is also to provide an enzyme with a handle with which it can hold this molecule and hold it in the right orientation for nucleophiles to attack the methyl group. So here's this elaborate leaving group, and but all that's really going on when you use S-adenosylmethionine is nucleophile attacks carbon on the backside, attacks the carbon, leaving group sigma star, and the leaving group leaves. So this is nature's solution to the fact that methyl iodide's too reactive and is toxic. Okay, so you will see this reaction. You will see rather this reagent or molecule in biochemistry. And now, when you see it, I want you to think back to methyl group attached to a leaving group. That's just an SN2 reaction. Okay, let's see. An example of an SN1 reaction is important in the synthesis of a lot of natural products, especially essential oils, and then also cholesterol. And it starts with a fairly simple molecule like this. This is a primary, this isn't an alkyl halide, but this is a leaving group. We have talked about, and we'll talk more about, how good leaving groups are conjugate bases of strong acids. This leaving group is called the pyrophosphate leaving group. If it left, it would leave as something that's resonance stabilized and bound to a magnesium ion, which tends to minimize the charge. You have been taught not to make primary carbocations except if they'd be resonance stabilized, and this is one of those cases. See the adjacent pi bond near where the leaving group is, and in nature what happens is this leaving group leaves to give you this carbocation, which is not a true primary carbocation, but is rather resonance stabilized. And depending on what nature needs to do, you can use this as an electrophile. A simple reaction is the leaving group comes right back in onto the tertiary carbon, and you get this isomer of your starting material. But there's a lot of other things that can happen. This is just a preview that's not important, but if you have the carbocation and you have an alkene nucleophile, one of the things that can happen is the HOMO of the alkene nucleophile can attack the LUMO of the carbocation on the primary carbon to make a new carbon-carbon bond. And what happens next is stuff that we'll talk about more actually in Chapter 10 on alkenes. But leaving group leaving to give you a carbocationic intermediate, that happens in biology all the time. It's involved in the synthesis of cholesterol and other steroid hormones in the body. And we'll talk more about that a little bit later. Anything you want to ask about that? So one of the goals of OChem is just to help you understand the world around you. And this is going on inside of you gazillions of times a second in your cells to keep them alive. And you didn't even know what an SN2 reaction was a couple of weeks ago, but your body's been doing it from the very beginning. So now you know. And there's more, but we'll leave it at that. Any things you want to know? Okay, so in Chapter 9, we're going to be dealing with alcohols as starting materials for substitution and elimination reactions. And right off the bat, we've got a problem that we're going to need to fix. And that is that this reaction generally doesn't work. So you might propose an SN2 reaction in which nucleophile attacks the carbon-oxygen sigma star and OH minus leaves to give you a new carbon nucleophile bond and OH minus. Unfortunately, that does not happen. And the reason why it does not happen, this reaction does not work, is because SN2 reactions require good leaving groups, and OH minus is a terrible, horrible, no good, very bad leaving group. In the sense that it is not the conjugate base of a strong acid. Now, being a good leaving group versus a bad leaving group is relative. And in 352, there are going to be reactions where you will see OH minus leave as a leaving group, but they're not going to be SN2 reactions. And there's going to be a very good reason why the OH minus leaves. But in this case, it's not a good leaving group in the sense that its conjugate acid, water, has a pKa of 16. We're going to see in general that good leaving groups are have conjugate acids with pKa's less than 0. Excuse me, sneezing. Okay, so we've qualified, or we've discussed Br minus and Cl minus and I minus as good leaving groups previously. Their conjugate acids are quite acidic. You can look up their pKa's, but that's an example. OH minus just doesn't make the cut. Okay, and what this means is that you can't do substitution reactions directly on alcohols. And so we need, and this is true also for not only for alcohols, but for alkoxides. Alkoxides and alcohols are similar in the sense that you just replace the proton with an alkyl group. I'm sorry, this is an ether. Ethers and alcohols are the same, is similar in the sense that you replace the proton with a alkyl group. But we similarly do not do a substitution reaction where we have the alkoxide as a leaving group because, again, its conjugate acid has a pKa of 16. So we're going to need a different strategy. Any ideas? Is there something you could do to turn the OH into a good leaving group? Stick an H on it, protonate it? Good. Very simple, elegant indeed, because if we were to do that, let's add an acid. So our strategy, turn OH into good leaving group. Sorry. Oh, yeah, that's terrible. Run out of space. So yes, protonate it is strategy 1. And so you could use a strong acid to convert the alcohol into the protonated alcohol. I'm going to call this the oxonium ion. And now, whereas OH was a terrible leaving group previously, which we're going to indicate with this red color for stop, now it's a excellent leaving group, which I'm sorry, red-green colorblind folks, but there we go. Now it's a good leaving group. And now we can bring in a nucleophile, and in this case, you happen to have one since you're using HCl. We learned in the last chapter that halides are included on our list of good nucleophiles. And we can go ahead and do the SN2 reaction to get the alkyl halide, and water. Okay, so go ahead.
For this specific reaction, or like this type of reaction, would you have to use a strong nucleophile base, or else would just deprotonate it again?
So good question. Would you have to use a strong nucleophile that's a weak base? Otherwise, you would run the risk of removing a proton. Yeah, and that's sort of guaranteed by the fact that you're going to use an acid to protonate the alcohol. If you're using an acid that is strong, its conjugate base must necessarily be a weak base. But the halides like Cl- and Br- and I- are nonetheless good nucleophiles, especially in protic solvents, in part because of their size and polarizability. Okay, so that works. Yeah, go ahead. Yes, chlorine is both a good nucleophile and a good leaving group. So you can, I mean, the question is, what does it do at this stage? And the answer is nothing. Do you remember what happens when you have a primary alkyl halide with a weak nucleophile, weak base? Nothing. Now, you could immediately take this on with another good nucleophile and go again. Why would you want to have chloro instead of alcohol? Possibly, I mean, the alcohol is a hydrogen bond, has a hydrogen bond donating group. The chloro doesn't. There may be situations in which solubility dictates you want one versus the other. In any case, organic chemists are always in search of the ability to do the same things through different methods, because there's a lot of reasons why you'd want to do this. One is just that if you're in the lab and you come up against something that you think should work and it doesn't, you've got another alternative. And then the other option, I guess, is I've never really seen the series Breaking Bad, but my 18-year-old son is into it, and apparently one of the major themes so far in the first season that he's watching is supply chain issues. So if you run out of an important component in the synthesis, if you have other alternatives, you can adjust. All right. Other questions? So this would work, of course, with any of the halides. I mean, you could take, if you wanted to make the corresponding bromide, you could take HBr. Your text, I don't think, shows you an example of using HI. Presumably that would work. Not sure. HI is really, really, really acidic, so it's probably difficult to use. But there's a problem with this method. And the problem is not apparent with primary alcohols. They work just fine via this SN2 reaction. But the problem is if you use a chiral secondary alcohol. So let's just start with this R2-butanol. And we'll use HBr, and what we get, we could have 100% pure enantiomer optically active, and then we do the reaction, and when we go to measure the optical rotation, what we find is that our new product is optically inactive. That is, it is a one-to-one mixture of enantiomers. Okay, what does that tell you? This would have been the expected SN2 product, but I get both, the one-to-one mixture, therefore what? Therefore, I had to go through, an SN1 carbocationic intermediate. The three dots there, I think I've told you before, are not Bilbo's dotting of an I, but rather the therefore symbol that I learned in 9th grade when we were doing geometry proofs. I don't know if you still do that, but that's what I learned. In any case, yes, therefore there must have been a carbocationic intermediate. And and that's consistent with an SN1 type mechanism. Okay, so what presumably happens here is that the alcohol gets protonated, and then you have the oxonium ion that is a sufficiently good leaving group that before Br minus can go in and attack, it leaves to give you this planar carbocation, whereupon Br minus can attack from above or below to give you both enantiomers. Okay, a couple of things here. Why does the OH group, why does water leave? I mean, why does the oxonium ion break apart? Why does water leave as the leaving group before the nucleophile comes in? Because you've been told that if you have a good nucleophile and a secondary leaving group, the mechanism should be SN2. Nevertheless, we observe that it's not here. And so this is a case where the hard and fast rules that you just learned you can find exceptions to them in chemistry. So I don't have a good explanation as to why this occurs, because again, if you were applying the rules that we just learned, you might think, hey, this should work no problem. In general, we will see that when you protonate an alcohol, for secondary and tertiary alcohols, the mechanism of going from the alcohol to the alkyl halide is SN1. All right, and that may be a point that you have to memorize. But it's more of a practical issue than anything else, because if you wanted to preserve chirality, if you wanted to have the desired enantiomer, you couldn't use this method. The second issue that's somewhat confusing and your text doesn't explain is that I've taught you that SN1 and E1 always compete, and nevertheless, I'm not showing you any E1 products. Why doesn't that occur? I don't know. Possibly because the halides are really, really weak bases. But as I said, I taught you in chapter 7 and 8 that we're always going to show both SN1 and E1 products together. Nevertheless, your text here in chapter 9 does not show E1 products for this reaction. I think you would be right to be aware of them. I think you would be right to draw them as possibilities, but your text doesn't, and so I'm not going to contradict your text. What that means is, on an exam, if I ask you for the products of this reaction, I'm not going to put elimination products down as distractors, because that would be evil. And I am evil, but I'm not that evil. Okay? Questions about that? Go ahead.
You keep saying, like, oh, we would have thought it was SN2, but it's not. What about HBr would make it SN2?
Well, Br minus we have on our list as good nucleophile.
Okay,
and we've said before that good nucleophiles don't hang out and wait for leaving groups to leave. Nevertheless, the data tell you that that's what's happened here. Yeah.
Isn't it always SN1 anyways, whenever, like, on the bottom of the...
Sure. With the tertiary alcohol, it would have to be SN1, but even with the secondary alcohol, there's evidence that it's also SN1. And that's sort of given without explanation or justification in your text.
We just have to memorize it.
Yes, in a sense, you'll have to memorize that detail, though I'm going to introduce a bunch of workarounds to avoid the SN1 reaction, and the very fact that we're learning that is going to help you remember that it did go through SN1. Go ahead.
Would that suggest that water falling off in that case would be relatively quick, because
Yep.
it doesn't give time for the Br, the halogen, to attack in an SN2?
That's right. The idea is the question is does that suggest that water is such a good leaving group that if it can, it leaves before the nucleophile can come in, and the reason it doesn't up here is because that would leave a primary carbocation. Yeah. So one of the things, this is messy, but science is messy, and frankly, so is life. And it rarely works out the way you think it should. Science doesn't care about the rules. It is what it is, and then it's up to us to observe and try to rationalize. So I'm showing you what happens if you, and in a very real way, what you would do if you were discovering this reaction in the lab is you would maybe start with the primary alcohol and say, okay, this works. I think this is an SN2 reaction. Then you would do it with a non-chiral secondary alcohol and you'd say, this still works. I bet it's an SN2 reaction. Then you try the stereocenter version of the secondary alcohol. You get this surprising result, and then you would have to retroactively rationalize why it was that way. The fact that you get a one-to-one mixture of enantiomers tells you that you had an achiral intermediate that had an empty p orbital above and below the plane of the page, which you could attack from above or below. So the bigger idea is, if given a result, can you explain what happened retrospectively, which you guys were able to do. Given that data, you were able to say, hey, it was probably a carbocationic intermediate. Now, for a predict the products question, you're going to need to remember that for secondary and tertiary alcohols, you proceed through an SN1 type reaction. Okay, other questions?
So is that not all SN1? It sounded like you were just trying to make a comparative difference.
Sorry, say what?
I don't know.
I'm so, for the primary alkyl halide, it has to be SN2 because the primary carbocation is too unstable. But for secondary and tertiary alcohols, the mechanism is going to be SN1.
Okay.
For protonating the alcohol to turn it into a good leaving group, and then the nucleophile comes in, that will proceed via SN1. Yeah?
With that achiral, secondary carbon, the reason why it knows the difference because it is doing SN1, but both products are the same.
That's right, yeah. For the achiral alcohol, you can't tell the difference between SN1 and SN2 products. So if you want to tease out the mechanism of reaction and you're a scientist, you have to design the experiment such that you could tell if your hypothesis were wrong. Okay. All right, so let's talk about workarounds for avoiding carbocationic intermediates. Workaround, oops. Actually, before we do that, I want to introduce something at this stage. Your book doesn't do this at this stage. It does it later, and then it's a question as to why it didn't do it previous. And so here's another piece of evidence that this reaction undergoes a carbocation, or rather passes through a carbocation intermediate. Okay, so here we have a secondary alcohol. And let's go ahead and use HBr. Presumably this protonates the OH group to turn it into a good leaving group. And then the good leaving group leaves to give you a carbocation. And if this were chiral, again, we would observe or expect to observe that because of the planar nature of the carbocationic intermediate, Br minus can come in from above or below. And you would expect as products, based on our new understanding that this is an SN1 reaction, we would expect to see both enantiomers. Okay, you with me so far? Does that make sense? But wait, there's more. We also observe an unexpected product, which is this. Dun, dun, dun. How did that happen? That's bizarre, right? The positive charge wasn't even on the tertiary carbon. The tertiary carbon here didn't have a leaving group on it. And yet, the nucleophile that comes in ended up there. We observed that as well. Go ahead.
So I'm assuming it just attacked the carbon, the hydrogen was knocked off, and the hydrogen just attached to the other side.
So the hypothesis is, could this nucleophile have done something to the hydrogen that knocked the hydrogen over? Well, that's a good hypothesis, but the problem is there's no real empty orbital here to speak of, right? I mean, we could have expected, and based on what, if we look at that carbocationic intermediate, we're already used to the fact of thinking of that beta proton as being lined up with the empty p orbital that's on the positively charged carbon, right? We've drawn the hyperconjugation thing before. Here is the empty p orbital, and then here is the filled carbon-hydrogen sigma bonding orbital. I'm going to draw in the phases that represent the LUMO of this molecule, as we've drawn them before. This is from the minus combination of the adjacent sigma bonding orbital with the empty p orbital. This is the minus combination. So we're already used to the idea of hyperconjugation, the filled electrons donating into here. The plus combination looks something like this, in which we'll draw the p orbital here. The plus combination of the empty p orbital and the filled sigma bonding orbital is this one. And from this one, you'd predict that there's some pi bond character between these two carbons as the electrons in this carbon-hydrogen bond delocalize a little bit into that empty p orbital. And in fact, if you take a step back and squint a little bit, what I've shown you on the bottom sort of looks like a pi bonding orbital, and what I've shown you here looks sort of like a pi star antibonding orbital. So the beta hydrogen, the beta proton, is already hyperconjugating with that positive charge. Now, let's imagine a process here. If the electrons in that carbon-hydrogen bond are already delocalizing, what if we slowly start to move that hydrogen nucleus over with its electrons moving over too? Okay, so we're physically going to pick up this hydrogen and move it to the right. And we're going to go through some intermediate transition state where I have a hydrogen that's got 2 electrons, but it's shared evenly between the 2 carbons. The whole thing has a positive charge, but that positive charge is sort of delocalized on the hydrogen and the 2 carbons. We would call this potentially a transition state. And if you were to draw what the orbitals looked like in this transition state, it would probably look something like this, where we're moving the 1s orbital on hydrogen somewhere between the 2 carbons. Okay? And you can actually do calculations and see this kind of transition state. Sometimes it's actually an intermediate, but the idea is that a hydrogen can lean over. And here, as I said, this is a new kind of bond that you haven't seen before. This is a 3-atom, 2-electron bond. It's really hard to draw a Lewis structure for it. But the way to think of it is just the hydrogen's leaning over and it's sharing its electrons with both carbons. which it was sort of doing anyway before due to sigma to P hyperconjugation. And then, if we continue on, we can get to the following structure. Oops. Where again we have an empty p orbital on a positively charged carbon, and then we have the adjacent carbon-hydrogen bond that's filled and is still hyperconjugating with the empty p orbital. Okay? Do you see how all these three situations are related? We're basically taking the hydrogen and sliding it over. We're changing who has the bond to hydrogen. We're changing where the positive charge is. This process is called carbocation rearrangement. And it's something that I have deliberately not told you about until now. But it's something that can happen anytime you have a carbocation. All right? What questions do you have about that carbocation rearrangement? Yeah?
I'm just curious, I don't know if this is important, why you showed us the minus combination. What does that represent?
The minus combination is what we use to rationalize why elimination reactions happen. The base / nucleophile dumps into the LUMO at the hydrogen, and then so that's how we do the E1 reaction. Yeah, it's the plus combination here of the sigma bond and the p orbital. That's the one that's easier to see how the carbocation rearrangement occurs. Yeah?
I feel like this is easier to understand with like an SN1 reaction because you're making that more substituted carbocation taken into
Okay.
but for E1 it's kind of hard to imagine why some like hydrogen would happen.
It's for an E1 reaction. It's hard to understand why what.
Why like a hydro shift or carbocation.
Oh, okay. Right. So yeah, let's talk about why this happens. And remember that the difference between SN1 and E1 is not in the carbocation, but what happens to it. So the idea is that carbocation rearrangement can happen quickly before either the nucleophile attacks or the base removes the beta proton. But one of the things you noted was that before we had, and maybe I'll just draw this intermediate again, but without the orbitals on it. Before we had a secondary carbocation, but after we have a tertiary carbocation. So interestingly, this process allows you to take a less stable carbocation and convert it into a more stable carbocation. And that's why it can occur. Now, these are both still high energy intermediates, and there is a difference in stability between the two. But the fact is both of these are present and in equilibrium with each other. So we need to show the products from both the first carbocation and then the rearranged one. Yeah?
Does that mean that that third product would be the favorite, would be the major product because it would favor having a tertiary carbocation?
It's a great question. Does that mean that this third product, the rearranged product, should be major because it goes through the more favorable tertiary carbocation? Possibly, and there's a bit of an issue here. When your text talks about carbocation rearrangement, sometimes it's not clear whether you're supposed to show only the rearranged product as the major product or not. I'm not going to push on that. I want you to show both the rearranged and the non-rearranged products, and I'm not going to ask you which is major. Now, if any of the products were alkenes, you could just say the more substituted one is the major product, because that's a pretty easy principle. But no, here I would not expect you to say which one of those dominated. Yeah?
Just to make sure I understand. So looking at the bottom of the equilibrium the secondary and the tertiary. What about a primary to like that top right carbon? Would that ever happen or be possible for any sharing or hybrid?
Okay, so you're wondering, could I rearrange this because, of course, this beta proton is hyperconjugating as well? Would I ever lean that over and make the carbocation go there? No, because it'd be a primary carbocation.
So just between secondary and tertiary.
Right. So carbocation rearrangements are possible between secondary carbons, between secondary and tertiary, and so on. This particular rearrangement where basically we are moving a hydrogen with its electrons over, we call this a 1,2 hydride shift. Because we move the hydride, or H, with its electrons from carbon 1 to carbon 2. And a situation where you can expect a 1,2 hydride shift is when you have, look at the context, you have a secondary carbocation adjacent to a tertiary carbon. And so that's a situation you need to be looking out for, because that's a situation where if you do a 1,2 hydride shift, you get to convert a less stable secondary carbocation into a more stable tertiary carbocation. Yeah?
You may have already talked about this, but what about a primary carbocation?
What about a primary carbocation? Oh.
Like, is that possible?
So you're saying, can I temporarily have this as an intermediate if I can quickly do a 1,2 hydride shift to get that? Is that sort of what you're asking?
Yeah.
Not in this semester.
Okay.
In 352, depending on, I never actually teach this in 352 because I don't think it's complicated enough and not important enough to deal with. But technically, yes, there is a spot in 352 in which something like that will happen. You don't have to worry about it now, and I pray you won't have to worry about it in 352, but you're rolling the dice on that one. Yeah?
And then just to clarify, is the carbocation rearrangement with the hydride shift just beneficial if it's like secondary to tertiary? Or can it be secondary to secondary or tertiary to secondary as well?
Good question. Is this possible if it's like tertiary to tertiary or secondary to secondary? That is, what if, I love the what if game. What if, could you do this? The way you draw the mechanism for a hydride shift is you take the electrons in the carbon-hydrogen bond and you shift them over to the new carbon that it's going to be bonded to. This would take a tertiary carbocation and convert it into another tertiary carbocation. In this case, I've chosen an example where both of those are identical anyway, so it doesn't matter. Yes, that can happen. I will show you an example of where it does. However, I will not ask you to predict that it happens unless you're able to get a less stable carbocation to convert into a more stable one. All right, so one situation where you're going to find this is when you have a secondary carbocation adjacent to a tertiary carbon. All right. And then another situation where you can find this happening, and it passes through a similar mechanism, might be if you have this secondary carbocation adjacent to a quaternary carbon. This carbon is bonded to 4 things. That's a quaternary carbon. In that case, I don't have a hydride to shift over, but I can shift a methyl group over in the same way that I can shift a hydride over. I'm not going to draw the orbitals for that. It's not necessarily important for what we want to talk about, but you could just think of this CH3 group hopping over to give you a more stable tertiary carbocation. And we call this a 1,2 methyl or a 1,2 alkyl shift. Presumably the transition state looks something like this, wherein you'd have the methyl group sort of evenly spaced between the two carbons with a positive charge delocalized, 2 electrons in a 3-carbon bond. That's the methyl group sort of leaning over, and then here is where it's leaned over completely, and you've changed who the methyl group's bonded to. So those are your two situations where I want you to look out for the possibility for carbocation rearrangements. Or rather, those are the two situations where I want you to be able to predict that a carbocation arrangement can occur. A secondary carbon adjacent to a tertiary carbon, and a secondary carbon adjacent to a quaternary carbon. Yeah?
And this is only for SN1 reactions, right?
That's for reactions that go through carbocations. So technically, this will happen prior to an E1 reaction as well. If we were doing an E1 reaction with a conventional nucleophile instead of the halides, where I told you for whatever reason we just get substitution products, you would draw the substitution products that come from both of these carbocations and the elimination products that come from both of them. Right? Okay, so that's carbocation rearrangement, and that explains why we get the rearranged product. So this is another reason why the SN1/E1 reactions are not that synthetically useful. If you're a pharmaceutical company and you need to make billions of dollars on a drug, and your synthesis method involves a step where you have to throw away half or more of your material, that's cruddy chemistry, and there needs to be a better way, and there likely is, and they discover it and so on. So rearrangements is one of the reasons why we might want to avoid the SN1/E1 mechanism. However, that's us synthetically in a lab. Biology has learned how to do this in a beautiful way that leads to products that we want. So what I'm going to show you now is something that you don't need to memorize or scribble to write down, but I do want you to see how each of these rearrangements leads to, yes, hurry. Nice scribbling. How the rearrangements lead to the final product. So let's see. Oh, apparently I didn't. That was lame, man. Dang it. Yeah, memorize all that, why don't you? Oh, you'll get to the Krebs cycle. Don't worry, that's coming in 352. All right, I'm actually going to draw, I need to show the unrearranged carbocation here so that you can appreciate sort of what's gone on. Dang it. Okay, so this carbocation is called the protosterol cation. And believe it or not, it comes from a linear precursor and forms all of that in a single step, which is wild. We'll learn about that later, maybe. But notice the difference between what I've drawn here for the protosterol cation and this rearranged cation. So, are there carbon groups missing? Well, let's look at the differences, and I'm going to try to highlight some of them. First, the positive charge is here on carbon 19 before the rearrangement. After the rearrangement, the positive charge is all the way down here on carbon 10. So clearly something has happened. Then with color, I'm going to highlight where things used to be. So, or this blue proton ends up here on carbon 19. This orange proton ends up on carbon 18. The pink methyl group ends up here on carbon 14. And the green methyl group here ends up on carbon 15. And notice that they keep their sort of stereochemical orientation. Notice that this methyl group was up prior to the rearrangement. It's still up after the rearrangement, which is consistent with how I drew the transition state for this process. It occurs all in the same one step, all in the same step, all on the same side. There's no hopping from this side down to that side. Okay, so what's going on here is a series of simple 1-2 rearrangements. So think through this. What would happen if this hydrogen leaned over and did the carbocation rearrangement? That would leave the blue hydrogen here, and what would be left on this carbon? Positive charge, which we could draw that intermediate, and you can if you want to. Good luck doing it in the amount of time instead of drawing that, we're going to show that this also happens. Is there a carbocationic intermediate here? And actually calculations have shown the free energy surface for this reaction is really flat, so the difference between intermediate and transition state is difficult to tell. So instead of saying, oh, there's a new carbocation plus a new rearrangement, I'm just going to show the next rearrangement, okay? That would put the orange proton down on this carbon and leave a positive charge here. Yeah?
Does it stabilize the molecule kind of like resonance?
Is it, oh, that's an interesting question. Does this stabilize the molecule kind of like resonance? Are these functional groups actually delocalized? That's a fascinating question to which I do not know the answer. So, cool. If there were a positive charge here, then I could lean this methyl group over to do a carbocation rearrangement, and it would end up on carbon 14 up. And then that would leave a positive charge here, and this methyl group could lean over and form a new bond there. Green would still be down on that other carbon, and that will leave a positive charge on carbon 10. And at that stage, we stop. So those are a series of 1,2 hydride and 1,2 methyl shifts. I'm counting 4 of them in rapid succession. It's a cascade. Yeah?
Could it have continued because there's a hydrogen and more carbon?
Sure. Could it have continued because you have another hydrogen and another methyl group? It sounds reasonable to me. For whatever reason, this is the intermediate that nature pauses at, and it's possible that for whatever reason the other carbocations are not as stable. There's probably something going on with ring and chair conformations here that we're not totally dealing with. But in any case, this intermediate is long-lived enough that a base from the enzyme removes a proton, and this is now the second step of the E1 reaction, and you get this neutral molecule that's called linosterol. And linosterol is a precursor to cholesterol, and there are 19 more steps. Which involve losses of methyl groups, moving around of double bonds, and nobody learns that even in biochemistry. There are people who do learn it and understand it, but getting to this point is really where you've seen all the cool OChem from 351. But I just want to point out that this carbocation rearrangement that seems so complicated is going on inside of you right now. And you can tell because you are alive. You need a lot of molecules to live, and among them are steroid hormones that are based on this core structure from linosterol, which we get through carbocation rearrangement. So, just a brief survey of steroid hormones. You have estradiol, testosterone, let's see, progesterone, which all share some structural features. Cortisol, a stress hormone, that's the one that kicks up and goes chronic when you're taking this class. Then there's the synthetic anti-inflammatory corticosteroids. Chances are, if you've had chronic inflammation or pain, you've been prescribed prednisone at some point or another. Cortisone, if you have a rash or an itch, you can get over-the-counter cortisone that you can rub on the rash. That will lower the inflammation. You've probably, if you've had a joint injury, you may have had cortisone injected into a joint to limit inflammation. Did that once on one of my shoulders. It worked okay. It was kind of weird. But and then let's see, you have synthetic progesterone analogs like levonorgestrel, which is a contraceptive. And then you have vitamin D, which is also from cholesterol. And it opens up in a reaction that you might learn about in 352 in the presence of UV light to generate this vitamin D3. And this is why people say you need sunlight to make vitamin D, because it's the UV light that causes this to happen. And also, let's not forget the gallbladder and bile salts. So this is an emulsifier that you secrete from your liver and gallbladder into your guts, and that's designed to emulsify fats so that you can absorb them. All of this coming from those carbocation rearrangements. Nature is nothing if not efficient with core structures, and from this one structure we get all this diversity. So naturally you want to know, will any of this be on the test? And the answer is all of it. You should memorize all of these structures. I'm just kidding, you should not, but you should understand 1,2 carbocation rearrangements, all right? So that's a good place to pause. We've set up why you want to avoid SN1 and E1 type reactions. The next hour, we're going to talk about how to do that and generate a number of new synthetic methods. So let's pause, and we'll come back in a bit.